So welcome students. So today we will be learning about intersymbol interference. In short, it is known as ISI. ISI stands for intersymbol interference. So let us discuss what is basically the ISI is. So you see, whenever we transmit some data from the transmitter, we transmit a sequence of ones and zeros, right? We transmit a sequence of ones and zeros. So this sequence reaches the receiver. Okay. So the question is that when it reaches the receiver, whether these ones and zeros are stays in its proper shape or not. That means here you see the ones are basically a rectangular pulse of a positive voltage and the zeros is a rectangular pulse of a negative voltage. So the main thing to the query is that when this rectangular pulses reaches at the receiver, whether when it reaches the receiver, these rectangular pulses still remain rectangular or become something else. So the answer is when this rectangular pulses, which is being transmitted from the transmitter, when it reaches the receiver, is no longer stays perfectly rectangular. Instead, it becomes somewhat like this. So this is a logic 1 when transmitted, and this is a logic 1 what the receiver receives. Similarly, this is a logic 0 what the transmitters, and this is the 0 what the receiver receives. So you see this pulses, ones or zeros, that the receiver receives is not a rectangular pulse. Instead, this pulses basically spreads out at both of its end. This pulses spread out at both of its end. And as a result of the spreading, what happens if I consider this time width of this pulse TB and the time width of this pulse, that is from here to here, this time width of this pulse to be TR, we will always find that the time width of this pulse is greater than the time width of this pulse, which is written here TR is greater than TB. So that means this pulse spreads out in time, and it spreads out in both the direction, the left direction and also the right direction. Similarly, for the zero transmission, same thing occurs. When this perfectly rectangular zero reaches the receiver, it becomes like this. Here also you can see the spreading on both the ends, left end as well as right end, and you can also observe the width of this pulse has become more as compared to its original width. Okay, now what happens when we transmit a sequence of binary pulses? So here is an example. See, I have transmitted 3 consecutive ones, 1 1 1, 3 consecutive ones from the transmitter. So when it reaches the receiver, how this will look like? So we can understand that when it reaches the receiver, it will look like this. Each of the rectangular pulse will be converted into this kind of pulses. So this is the first one, this one, this is the second one, this one, and this is the third one. Now if you look into the diagram, you can understand that due to the time width spreading of the pulses, the tail of the pulse, what is tail? This is called the tail. This and this is the left tail and this is the right tail. The tail of any pulse will enter into the region of its neighboring pulses. Similarly, if you see this pulse, its tail has entered the region of its neighboring pulse. So in other way, what we can say that if I take this pulse, so in this region, not only this pulse is staying, not only this pulse exists, but the tail of the right tail of its left pulse and the left tail of the right pulse is also entering as an intruder at the region where this pulse is set. So what will happen as a result? So as a result, this pulse will be getting corrupted by the presence of the tail of its neighboring pulses. That means if I want to estimate the height of this pulse, I may get an erroneous result, because now I'll not only be estimating its height, but due to the interference of the neighboring pulses, this height can get changed. So that means this pulse can become corrupted and can become wrongly detected as 0, if in the case like that.